All right, let's get started. So, how do you determine all those equivalent circuit parameters? They're not easy to get, but you have to come up with a way of taking this big hunk of metal that rotates with windings and being able to come up with an equivalent circuit. We did the equivalent circuit for the transformer, right? We did some no load and load loss tests. We did some tests for the synchronous machine where we did open circuit and short circuit characteristics to get those. So similarly, we have to do the same thing with our induction machines, and we're kind of limited as to what we can do. We can do a couple of tests from a perspective of applying a voltage and looking at speed, but that may not necessarily be all that useful for us. So if we could actually run the test and get the actual curve, we might be able to get something, but that might be very difficult to do as we determined in lab, right? Remember in lab, we tried to get that torque and it was really difficult to get those peak values. It's almost impossible. Industry's not going to have any more luck doing it than we are. But what they do is a bunch of tests. So let's do the same tests that we did for the transformer because they're pretty much the equivalent circuits. Okay, we're going to do an open circuit test and a short circuit test, or we're going to do a no load test and a load loss test. What would be the equivalent for an induction machine? No load test just means run it at very light load, almost none. So you just have the friction and windage losses. The short circuit test, that's the harder one. So you're trying to short out the secondary of a transformer. It's already in an induction motor, it's already short circuited. So the only thing that you can do that similarly looks like it is you make sure that the slip is as low or as high, I should say as high as possible. So the only thing that exists in your rotor equivalent circuit is the rotor resistance. And how do you do that? You make sure that this machine doesn't spin. So you lock the rotor in position. You literally put some sort of a shaft maintaining device, you bolt it in place, and then you run your tests. Now, we have to do one additional, yes, go ahead.
Instead of locking the rotor, what if it's a heavy load?
A heavy load, what's the difference between a heavy load and locking the rotor? Isn't a heavy load or lock rotor a really, really heavy load? Yeah. The reason why you don't want to do just a heavy load is because it's difficult to replicate the slip, right? So if it's rotating, even if it's rotating slowly, you're not going to get a slip of 1. So that R2 divided by S you get in the secondary circuit, all bets are off, right? You can't get there. So if you know that it's not moving, R2 over S becomes R2 over 1, and then you know what the rotor resistance is. Okay? And then the only other thing we need to do, which is a little bit unique, is we're actually going to do a DC test to figure out the stator resistance. So that's a modification from the transformer circuit, but we did do a DC test on the synchronous machines, if you remember, right? If we were trying to calculate the armature resistance, we put a DC piece of equipment on there. We ran it without the machine running. All the inductors get shorted out, and we're basically left with some resistance. So here's a DC test, just exactly the same as the DC test on the synchronous machine. We take a variable DC, we run it into an ammeter and a voltmeter. We put the current limiting resistor just because we're trying to protect it. Because remember, the induction machine has a bunch of inductors associated with it. So you're going to get some transient decay associated with it. So when you first energize your induction machine with DC, it's going to look like even more of a short circuit over time than was necessary. So you're going to limit the current just to sort of provide some sort of protection. And then you measure the current and the voltage, and you should have the ability to calculate the resistance. In a Y-connected one, we can see that these two are in series with each other, just like on the synchronous machine. And if they're delta connected internally, we have to figure out how to break out those terms, just like we did before. So in a Y-connected machine, we just divide it by 2. We take our DC voltage, divide it by our DC current, and then we get a resistance. We divide that number by 2, and that gives us each of these individual resistors here. If it's delta connected, we've got to do a little more work, right? Because now we have that series parallel combination. So you have R1 in parallel with half of, in series with half of R1. So you have R1 plus 0.5 R1 equals VDC divided by IDC. So 1.5 R1 equals VDC divided by RDC. So R1 equals VDC over 1.5 times IDC. It's exactly the same as how we did that approach when we did it for synchronous machines. Okay. And notice it's a 3-phase machine. So I've got 3 windings, but with DC, I do not have 3-phase. I only have a plus and a minus. So that third leg, even if it's connected in DC, I'm not going to run a wire to it necessarily. It just that, it just have to leave it open like that. And you just have to figure out the calculations there. So that's the calculations that we have here. 1/2 or 3/2 are DC. No load test. You're allowing the motor to run with no load connected to the shaft. You're allowing it to run as basic and as simply as possible. So you basically only have friction and windage losses, which means that my slip is almost, but not exactly 0. It's 0.001 or something really, really small. And does this look familiar to you all? Kind of the 2 watt meter method that you do. So the reason why you do this in the real world is because you want to get an exact measurement. What we did in lab the other day was like, you know what? 1 phase is close enough to get the realistic results. We don't have to be exact, so we'll just use a single phase. But if you want to be more accurate, you can go with 2 watt meter, or you can even get 3 watt meter methods. It just complicates the amount of wiring. Oh, by the way, let me ask this question. Why is it that when I put DC, I only get R1? Did you see over here? It just had R1. Why don't I have R2 or RC in that circuit? Well, but this equivalent circuit has an R2, right? That's reflected over to the rotor circuit. So why don't I have RC and R2?
That's AC voltage.
Say that again?
That's AC, not DC.
Well, a resistor doesn't care if it's AC or DC, right, Adrian?
It doesn't, but the circuit itself would, right?
Sort of. You might be on the right track. You guys are right there. You're almost right there. Just tell me what the simple answer is. The simple answer is, Mac. Got it. Inductor shorts out over DC, right? So this just goes to be a short circuit, as does that. But you all were saying sort of the same thing, like what's happening with the AC. The AC is giving you that changing magnetic field, which allows that inductor to actually be an inductor. But DC over time to an inductor, the inductor just shorts out. So the only thing you're going to get is R1. You won't get R sub C or R2 in your final circuit when you do the DC test. And the problem with R sub C is there's no easy way to get R sub C. So you're going to have to estimate it based on core losses, some method to do that. We're not even going to be able to calculate what that is. All right, so let's go back to the no load test. So we know that S here is really small, 0.01, 0.001. So 1 minus essentially 0 is 1. Divided by 0 makes this an open circuit, right? And what we see is because of that, this value becomes much, much greater than R2. And because this value is much, much greater than R2, it's also going to be much, much greater than X2. So our final circuit can just be replaced by getting rid of all the inductors in our rotor circuit because they're small, because it's running at synchronous speed. So that rotating magnetic field is really small. And all we have is a resistor here that has some friction and windage. Okay? So if we move our core losses into our friction and windage losses, we end up with this. R1 plus friction and windage and some core losses. Okay? So all the input power has to be consumed by the losses in the motor, plus the copper losses and the friction and windage losses. We're going to ignore any rotor copper loss because, again, that R2 times 1 minus S over S is essentially negligible. So our input power is going to be our stator copper losses plus our rotational losses. Then our equivalent impedance just becomes approximately X1 plus XM. And now what you need to do is you have to have some way of solving for that. So going back to our circuit, what we're going to look at is we have a way of determining what this is. Now we have a way of combining and determining what X1 and XM are equal to. All right. So our equivalent impedance is we're just going to approximate it. We're going to say R1 is so much smaller than X1 plus XM. And it's also so much smaller. The core losses are so much smaller than that value. Then we're going to assume that this, oops, going to go backwards. This is going to be equivalent to a short circuit. And this is going to be equivalent to an open circuit. So all we have now is X1 and XM in series with each other. So when you do the no load test, all you can get is X1 plus XM. Can't get anything else. You can only get X1 plus XM. All right, so we have that. And we have R1. We don't have R2. So let's see what we have. We have R1. We have X1 plus XM. That's basically it. We need R2 and X2. Is that all we need? Not really. Like I said, that's really difficult to find as our core loss.
It'd be nice to know what X1 is.
Yeah, we don't know X1 nor XM. We know the series combination of those two, but we don't know them individually. So we've got some additional work to do. We need to figure out how to pull out those parameters. So let's do our locked or blocked rotor test. And our locked or blocked rotor test means we're going to make it so that this value of slip is going to be equal to 1. So now what we have, and again, assuming that our value of XM and R sub C are much, much greater, these become open circuits. So now all I have is this part right here. I have R1, JX1, JX2, and R2 exclusively. So now I can start to figure out which one is real power, which one is reactive power, and start associating terms. But ultimately what I see is the magnitude of my locked rotor impedance is going to be some real part plus an imaginary part. My real part is going to give me the series combination, R1 plus R2. And my imaginary part is going to give me the series combination of X1 plus X2. So I had R1 from before. Now I have, and then I had X1 plus XM. Now I've added R1 plus R2. And now I've added X1 plus X2, right? Those are the additional parameters that I've gotten. That's all I've gotten was X1 plus X2, R1, R2. But I recognize, I already know what R1 is. So R2 is equal to our locked rotor resistance minus R1. I know what R1 is, so I can pull out R2. Can I do the same thing for X1, XM, and X1, X2? How many equations? I know the answer, right? I know what x1 plus xm is, and I know what x1 plus x2 is. How many equations? How many equations? 2 equations, and how many unknowns? 3 unknowns. So I don't have enough information to be able to calculate xm, x1, and x2. I have to do something else. And that's where I go to this step. So this is just basically using, how people have designed these machines over many, many years. They have a ratio. If you know what x1 and x2 are equal to, or the combination is equal to, then you can approximate each of those by using this table. The most common piece of equipment that we're going to use is a NEMA Design B, which has 0.4 X lock rotor for R1, or X1, sorry, and 0.6 X lock rotor for X2. Once I have the table, I've got R1, I've got R2, I've got X1 plus XM, and I've got X1 plus X2. Now I can use the table to pull out X1, X2, and once I have X1, then I'm able to calculate XM. So I have all the elements of my equivalent circuit. The only one that I'm missing is R sub C. And there is no easy test to get R sub C.
So the in the table, x1 is the 0.4.
It's 0.4 of the XLR. So remember, X1 plus X2 is equal to XLR. So X1 is equal to 0.4, and the rest is equal to X2.
Just the ratio.
Yep.
So which means for this, we need to know which type of motor we can.
The design characteristics, yes. The vast majority of ones you'll come across in the industry are design B. Not all of them, but the vast majority.
Feel that when they on the rotor sheet with the motor, it stays which design is it.
Yeah, the nameplate, but normally you would specify a motor design, and you would specify if you had different characteristics, like if you wanted a steeper drop off, you'd go to NEMA Design A. If you wanted the standard one, which has a lot of starting torque, a pretty good lock rotor, a breakdown torque, and then fairly efficiency, you go with Design B. If you want all your starting torque to be available at the beginning, when you start it up, so you want your pull-out torque to be at the start, you'd go with a NEMA Design D. So the big one would be like if you're doing a fan. So if you think about a fan, does a fan seem like it's hard to work? Or is it hard to make a fan work? It's just pushing air, right? Should be a piece of cake. Except remember, the shaft maybe is a 1/2 inch diameter shaft. Think about the fan blades way out over here. That takes a lot of energy to get that to rotate. So if you want to get a fan, a decent sized fan up and running, you might actually want it to be a NEMA Design D, because it might take you 5 minutes to get that fan running with a NEMA Design B. And why is that a problem? Anybody have a problem with that? Doesn't necessarily take more energy. What did we say, or we witnessed in lab when you were running at really low speeds? What did we see about the current? It takes a lot of current, doesn't it? And it's not putting out any real torque. So running a motor for 5 minutes at nearly lock rotor current is a sure way to spell doom for that motor. So if you get it up to speed quicker, you don't need as big of a rating of the piece of the motor, and you might have a little bit of an efficiency penalty because you're not running at the same level of slip. But instead of taking 5 minutes to get up to speed or upsizing the motor, I can go with the mandatory motor size that I need, and then just run it at 1 minute because it gets more torque available, spins it up faster. Avery, do you have a question? Okay. Yes, sir.
Can you just go back to where you find the lock rotor test?
Yep. There's a typo here. This should not be that should not be magnitude. That's the real part and the imaginary part. So that should just be Z. So let me fix that.
How do you measure those?
Go ahead.
Does it show in the slide before?
Measure what?
Like how you find the Z from?
V times V divided by I.
Okay, so you're measuring your V.
All these tests, right? If I'm going to do block rotor tests, I apply voltage. I measure the current, but that voltage has to be across all three phases because I want that to be under normal operating conditions. All right. Anybody have any heartburn with these tests? Make sense? Happy with them? I hope not. Why? Didn't I just tell you you don't want a motor to be running at 5 minutes at heavy loaded conditions? You think that's a good idea to lock this in position and run it full voltage at full frequency and then pray it doesn't burn out? Some of these are only going to last for like 5 or 10 seconds before they start to get some damage. So might not be a great idea to do that. So do you have a suggestion of how to do that differently? Do you decrease the voltage? We don't decrease the voltage because if we decrease the voltage, then what ends up happening is we don't transfer that magnetic energy from the rotor to the stator to the rotor very well. What's another way that maybe you can make it less painful for the machine? Avery, you have a question? You have a comment or? Well, this is the lock rotor test. We got to do it under lock rotor conditions. So no load would be perfect. No load is like the machine's happy to run there all day. That's what we did in lab, right? Remember we did our tests and then we backed off completely to let it cool. And we saw how the current dropped way down and then we had airflow. So all was right with the world. But we have to do the block rotor test. So we need to provide full voltage to make sure we transfer that magnetic field. Is there anything else you can do? What does an AC voltage have? It's two parts. Magnitude and frequency. The whole thing about an induction machine is the higher the difference in speed between that synchronous speed, the synchronous speed of the machine and the actual operating speed, it generates a bigger voltage and current on the rotor circuit. So how do you make that smaller? You run it at a lower frequency. So instead of running this at 60 hertz, maybe you run it at 15 hertz. So when you do these block rotor tests, this voltage here is not running at 60 hertz. It's running at way less. And that means the motor can survive and you can do more data. So that's why these are corrected. You'll notice here, there's an F rated versus an F test. So the F rated would be the 60 hertz and the F test is whatever frequency you have. And the reason why we have to adjust, well, why don't we have to adjust the resistance? Why do we just adjust the impedance?
It doesn't care. AC, right?
Say more. Isn't frequency built into inductance? Resistance, it's not built into it, right? Resistance is resistance is resistance. So there is no frequency component to adjust with resistors, but with inductors, you certainly have a frequency component. Now, if you really wanted to get hardcore and say, well, what about the skin effect, Paul? You're running at a lower frequency, so skin effect is going to be less prevalent. Yes, that's true. But at some point, you know, how exacting do you need to be? If you really want exact results, you'd have to do a whole bunch of different things. This is just, you've got 500 motors coming off the assembly line. You're testing each one to give it to see what's going on. So you got to do some fairly quick tests. So all you need to do is you just adjust the inductance just on the lock rotor test. You just adjust its frequency by the ratio, the rated frequency divided by the test frequency. Example time. We have, again, these are ratings, 7.5 horsepower, 4 pole, 208, 60 hertz. Now we need to start thinking about NEMA design, right? So before we didn't care. Now we actually do care about the design characteristics. So this is a NEMA design A, which allows us to go into our table and pick out the correct values for X1 and X2. It's Y connected and it has a rated current of 28 amps. So we really don't need this other than, you know, we were trying to maybe see if we were getting full values. We really don't need this. We need the 60 hertz. We need the 208. We need the design A. We need the Y connected. Do we need the fact that it's 4 pole to do any of these calculations? What's that? No, we don't. Nothing is based on synchronous speed, right? All these calculations are based on those values, so we don't need it. All right, so let's go ahead and copy this, and then we'll bring it into whiteboard. What's that? I copied F.
You didn't copy the whole thing.
Don't I have enough information here, though? All right, so Y connected machine, which means our windings are connected like this, right? So for the DC test, I know I have an R1 and an R1. So here's my DC test. I've got 13.6 volts, and I've got 28 amps running through that. So my R1, or 2R1, because I have 2 of those in series, is equal to 13.6 volts divided by 28 amps. So R1 is equal to 13.6 volts divided by, if I did that correctly, the 56 amps. DC test. Now let's do the no load test. Under the no load conditions, what does my circuit look like? I have R1. I have JX1. And I only have JXM, right? RC is out of the picture because it's so big, it doesn't have any influence. And then our R2 over S is so big that we can neglect it. So no current we're going to assume is going into the rotor equivalent circuit. And so here's our circuit. And so now we have our voltage, 208 at an angle of 0, and our current, 8.17. What's the angle of the current? Zero degrees? Nope, it's an AC. 90 degrees? Yeah, I got to do my power triangle, right? Here is 420 watts. And here is, oh, sorry about that. 8.17 times 208 volts, correct? Is that correct? One yes. Anybody else say yes? Yeah, this is 3-phase, right? So that 420 watts is the total power consumed. So if I'm trying to get the total S, I need to multiply, because that's a line voltage, the 208 volts. And I'm going to assume that the line, well, I don't assume it. I know that the voltage, the phase current and the line current are the same. So it's square root of 3 times 8.17 times 208. Now I should be able to calculate theta as equal to the inverse tangent, or inverse cosine, sorry. In my other class, I was talking about tangents, so I'm thinking about tangents today. So that's going to be equal to the inverse cosine of 420 over the square root of 3, 8.17, and 208. And that angle is going to be stuffed over here, except we need to keep in mind, what type of a motor is this? It's an induction motor. So if you had to hazard a guess, what power factor would you expect this to be? Lagging or leading? Lagging. So don't forget, because our voltage here is at an angle of 0, we need to make sure that we have the negative angle there. Are there any other errors on this workbook? Or are you feeling good about it? Since I'm asking you, there probably is, right?
Sure.
So say yes, just for the sake of that. Very good. Where's the error then? You've been warned about this at least half a dozen times this semester.
The even the 421. The three-phase also.
That's three-phase, yep. Well, the negative kind of gave us the conjugate, so by putting it there, we do have the negative angle. So we kind of have that built in. Any other? Maybe I'm wrong. Didn't get a ton of sleep last night. So did I make a mistake? What type of equivalent circuit is this? What type of equivalent circuit is this? What's that? This is the no load test. What type of equivalent circuit is this? Per phase. So why were you okay by letting me put a line voltage there when I wanted a per phase equivalent circuit? Why didn't you tell me I needed the square root of 3? Haven't you been warned at least half a dozen times about doing that this semester?
Some other people probably didn't also sleep.
Ah, fair enough. Yes, sir. Well, because the power triangle is S is 3 B phase I phase, right? For three-phase power. Or we use the second equation. Over here, everything has to be in a single phase equivalent. Why is that? Because there's no such thing as a three-phase resistor. There are 3 single-phase resistors connected in delta Y, but there's no such thing as a three-phase resistor. So this entire circuit here, all has to be in single phase. So now you can solve for Z no load as being equal to 208 at an angle of 0 divided by, I said 0 when I wrote theta. At an angle of 0. I'm going to divide that by 8.17 at an angle of minus, and for lack of a better term, I'll call it no load. And that's going to give me R1 plus X1 plus XM J term. I don't care about R1 because I already solved with DC. So I'm not going to even look at the R1 value. I'm just going to focus on the DC term. Yes, sir.
Going from line phase to final phase.
The 208, you mean?
The 208, that changed the
Can we do the power triangle above with the, 3 times. The 8.117.
Nope, because I can use either one of those equations. I can either use 3 times V phase I phase, or I can use square root of 3 times V line I line. If you wanted me to do it this way, then I can say that that's equal to 3 times 208 divided by the square root of 3 times 8.17, right?
Yeah.
But what is 3 equal to? Square root of 3 times theta is 3. So if I do that, that square root of 3 term cancels. It's in the denominator. So it's the same thing.
Okay.
Question?
Are I phase and line lines in this equivalent circuit?
Has nothing to do with the equivalent circuit. It has everything to do with, in a Y connected circuit, does I phase equal I line? So it's not the equivalent circuit, it's the Y connected motor. That's why it's the same. So that's going all the way back to whenever we introduced chapter, was it 2? Maybe it's chapter 1 or appendix A, I can't remember. But that's all the way back to when we introduced 3-phase systems. So now we have X1 plus XM. You have a question, Drew?
Yeah, why do we do a DC test so we can just get R1 and 3?
Because it's actually more accurate to get you're going to get slightly different results here because of measurements and power factor and all that stuff. So it's usually more accurate just to do a direct DC. You're directly measuring what R1 is. All right, so now we have X1 plus XM, but we still don't have the ability to calculate. So we're going to have to do our locked rotor test. And if you look at our locked rotor test, all that gives us, is this R1, R2, JX1, JX2. The voltage is 208 at an angle of 0. Oops, 25 volts. So this one I actually ran it at a lower voltage, which I don't believe is usually the case. We divide that by the square root of 3 because it's still a 3-phase voltage. And our current is 27.9 at an angle of minus theta. Now we'll call it locked rotor because we know where that theta comes from. And the only other thing we have to know is that the frequency is 15 hertz. It's not operating at 60 hertz. It's operating at 15 hertz. So it's exact same thing. Same thing we did for transformers too. We have to do a power triangle. And our P is 920. And our S is the square root of 3 times 25 times 27.9, right? And then our theta locked rotor is going to be equal to the inverse cosine of 920 over the square root of 3 times 25 times 27.9. That angle gets put into there. Don't forget the negative. And now we can solve for Z locked rotor equal to 25 at an angle of 0 divided by the square root of 3 all over 27.9 at an angle of minus theta locked rotor. That's going to give us R1 plus R2. And it's also going to give us those. If you want to be exact, then you would do it this way. You would spell it all out. If you want to be approximate, you could just say that R2 is small enough. You know, you can ignore it, but let's just do the full Monty version here. So now you have X1 plus X2, X1 plus XM, R1, and R1 plus R2. So at this point, you can solve for R1. Pulling it out there. And to be able to solve for X1 and X2, I got to use my NEMA design. So my NEMA design for type A, they're both the same. So since it's a NEMA design A, we have X1 equals X2 will equal to your locked rotor current divided by 5, divided by 0.5, divided by 2. No. Now, one other thing we need to do is that's X1 and X2, but that's at 15 hertz. We need to correct that to 60 hertz. So we need to multiply that by our rated frequency over our test frequency. Because again, it's frequency dependent. Next step, XM is equal to XM plus 1 minus X1 minus the X1 we just calculated. And now we have our equivalent circuit, which I'm waiting for the moans and groans. I did it in MATLAB. Why did I do it in MATLAB? To make you laugh and torment you? No. Keeps me honest, right? If I just put the results on the slide, you can say it's all BS. You're just BSing us. See, in a MATLAB, that's the same thing as doing a calculator, right? Expect more from me, professor. Make them prove it. So this is the truth, right? This is no lies. This is all here. So take a look. I showed you the DC test, how to calculate R1. I showed you the no load test. We have all the values over here and how I calculated those values. And even look what I called it. X1 underscore XM is equal to the imaginary part of the Z that I calculated with the no load tests. That's exactly what we did before. When we did this here, that's what I specified, right? This is the imaginary part. So I'm just pulling that out. But I don't actually have X1 plus XM individually. I have them combined. So I need to break them out. So I need to go through and do my locked rotor test. Enter my data, get my angle, add it to my current. Notice the negative sign. Calculate Z, pull out the real and the imaginary parts to equate R1 plus R2 and X1 plus X2. Now I corrected it. So I corrected the frequency here. So that's 60 over 15 because 60 is the rated frequency. Then I pull out all my parameters. There's R2, there's X1, X2. Now I have XM. So I'm going to run it to here. And let's get this out of the way. Where is MATLAB? Oh, here it is. And there are your values. Here's R1 from the DC test. R2 I got from the DC test and the locked rotor test. X1 and X2 I got from the locked rotor test plus the table based on the NEMA design. And XM I got from the no load test with the fact that I already got X1. So my equivalent circuit is, so here is R1, JX1. I'm not going to bother showing R sub C. I don't have a good way of calculating it, and usually it's pretty high anyway, so I can ignore it. So this is R1, which is equal to, well, I just paste it over here. Oh, where did you go? So R1 is 0.24. R2 is equal to 0.151. Don't forget that's over the slip. That's going to vary based on the speed, so that has to be variable. XM is 13.98. X1 is equal to 0.6706. And because it's a NEMA design A, they're both the same. That's my equivalent circuit. That is part A of the problem. Questions on how to get part A? awfully quiet. Does that mean it's perfect understanding?
I don't know about perfect. Probably gonna be some questions that'll come up after the information digests, but
Fair enough.
as for right now, right?
Okay. Thanks, Adrian. Mac, you have a question?
So with the synchronous motors, we had the different currents that we tested, we had like the air gap. What was the stuff that we did, that's not relevant for these type of motors?
No, and the reason being is we did that when we did a synchronous machine. So we actually had a field current that we were separately controlling that was giving us a voltage. So we had to do different way. We had to adjust the field current to get a bunch of different curves so that we could get those values. Over here, the only thing we can adjust is the load. Can't adjust anything else. So we only have two options: run it under lock rotor conditions and run it under block rotor. You can actually run it at different slip values, but it doesn't really give you a lot of information. You're gonna have to do some additional work to get there from here. So let's just do these two tests. How do you do B? For the slip at pull-out torque. This is an easy one. That's ST max. Remember the equation we did last class? How to calculate ST max? And this is T max. Just use those two equations to calculate it. I did those as well.
But you don't have the skip them.
I don't need the slip. Now, for part B, I do need to know it's a 4-pole machine, right? So now I need the fact that it's a 4-pole machine to calculate slip and all that stuff. I mean, I would need it actually for a mega sub S, only for the torque, not for the slip. But your slip, right? We have an ST max equation that we developed last class. That's when we have max power transfer. So we were just calculating there. I did it over here because I can't remember those equations. I'm glad nobody asked me to remember it. I just pulled it out over here. I solved for V Thevenin, R Thevenin, X Thevenin, and I can solve for this in any order. I can do the slip first, or I can do the torque. Doesn't matter. Either one of these is fine. So I will step all the way through. And my slip occurs at 11.1%, and my max torque output is 66.1 Newton meters. And that would be fine. That's what you did on the homework, most likely, right? I'm giving you more than what you bargained for. So I actually did the full Monty one where I did 1,000,000 calculations, or how many zeros is that? 1, 2, 3, 4, 5, 6. I did 1,000,000 calculations. That's why this is up to 1,000,000. So I wasn't lying. I did 1,000,000 calculations. And I allowed my slip to go from 0.01 to 1. And I did my 1,000,000 calculations. And now I'm going to plot that. And let's see how close it is to a slip of 11 and 11% approximately. And then our max torque of, what did we say, 66? So let's see. Click right here. So I said 66 with the hand calculation. This is almost the same, right? 67.2, pretty close. And the speed is 1596. Can you calculate what the slip is? Oop. What's going on? The slip is equal to NS minus NM all over NS. We know what NS is supposed to be, right? It's a 4-pole machine, so this is 1800. So we can solve for that. NM equals 1 minus S times 1800. If we plug in 0.11 times 1800, we should get around, what did we say it was, 15. Oh, what happened? It just disappeared. Was it 1596? So what is 1 minus 0.11 times 1800? Hopefully around
Yeah,
1600, so fairly close. I also think if you look at MATLAB, remember I did that index stuff? So I just did I did the indexing and I pulled it out and I calculated it as 11.3% versus 11.12%. Okay, but the slip max one over here, if you look at the script file, I actually display that over here. So I actually did the calculation we just did to look at what was, just to be able to confirm the two, see if we get the same results. So I know you hate MATLAB, but I didn't do a lot of MATLAB until I needed a calculator. So if you'd rather see me sit there and do this, conceal everything, I can just make stuff up. But with MATLAB, you can actually see it go through. But all these calculations here, all this is the work that we did to get those results. Questions?
Maybe not really related. It's related, not really related. Can you go through your MATLAB code? Because you did the
Gibberish. Ouch.
like in the code, in the for loop. In the for
Do you
loop.
do you see any of this stuff here? Does all this stuff make sense?
Yes.
The only one some people might get. So this right here is a theta. That's just taking the inverse cosine of the P over S. The only thing that you might be a little bit unaware of is this one right here. But we've actually talked about that before. This is Euler's identity. Euler's identity is basically doing, that's all MATLAB is doing, ME to the J theta. Your calculators, you just do this.
Yeah.
MATLAB doesn't have that same capability, that pretty way of entering it in. So you just have to go ME to the J theta. That's what that line is there. Now, the rest of it is just more calculations, right? Just if you were doing it in your calculator, all the steps. The only thing that starts to get difference is here. So what I like to do with MATLAB is we did 1 million calculations, and I don't want to sit here and do 1 million calculations. I want MATLAB to do 1 million calculations. So I automate the process by doing a for loop. So how I start is I let slip be my variable that I want to calculate every time. Why do I do that? Because the equivalent circuit over here is a function of S, right? That's the only thing that can vary. So I want MATLAB to do a calculation at each individual value of slip that I want it to. So in MATLAB, I say, let's go ahead and set up a bunch of slip values that start at 0.01 and end at 1. And I want there to be a million linearly spaced points. That's what lin space stands for. You are literally spacing out between 0.01 and 1, however many points you have. You can specify 10, 5 million, whatever you want. So I'm just saying, I want there to be 1 million points linearly spaced between 0 and 1. Now I do a for loop and I make it so that it's a function of slip. So in MATLAB, you can use a code called the length of the slip. So if I wanted to change this to be 10, it'll automatically calculate the 10, there's 10 numbers in slip. So I don't have to keep track of how many in there. It just automatically does it. So it's a for loop, 1 to however many slip values you have. That's essentially what that means. Does anybody here not know for loops? Anybody here not had a class in basic programming? For loops, if loops? A for loop basically is do something until you reach the end of whatever value you told it to do. Then I calculate my Z matrix. This is that matrix that we did before. We did I1 and I2 loop equations. Then I calculate my current matrix, which has I1 and I2, by inverting my Z and then multiplying it by my phase voltage, which we said was 208 over the square root of 0. Over the square root of 3 at an angle of 0. And then there is no external voltage source on the secondary circuit, so that's always 0. Then I pull out my rotor current. Then I calculate, if I need to, my rotational speed, my actual rotational speed. Then I just calculate what the output power is going to be, because my torque is going to be equal to my converted power minus my air gap power minus any rotor copper losses. I am not including any rotational losses in here. Why not? because if you look at the problem description, there is no detail on the rotational losses. So I'm going to assume that there's 0. If they change, all I would need to do would be to subtract from this P out equation the rotational losses. Now, why is that a difficult approach? Because rotational losses are going to vary depending on the speed. So if I'm trying to calculate the slip all the way from essentially 0 speed all the way up to synchronous speed, I would actually have to have some way of, varying what that rotational speed is. But since we're not told it, we don't have to worry about it. We'll make it that way. So, good question this morning. It's I squared magnitude R, the magnitude of I squared, not I, or the I times the cosine of theta. It's the magnitude of I squared R. That's what I have here. I've got 3 resistors, so I've got to get all the power loss. I multiply that by whatever the output power is. That's R2 times 1 minus S over S. If you don't like it, you could have also just done 3 times I2 R2, and then go ahead and then that would be my rotational copper losses, and then do all the converted power. But this is just easier. Essentially, all I did was when I have these 2 resistors, this is my rotor, this is R2, and this is the R2 times 1 minus S over S. This is the converted power that's mechanical. So that's the actual power that gets converted. That's what that resistor is equivalent to. So I just did that calculation right off. And then I just calculated torque. Power equals torque times omega. So torque is equal to P divided by omega. And then I end the for loop. And it'll keep doing whatever's in that for loop until it reaches whatever the length of that is. In this case, it's 1 million. And then I just plot it. So we don't like to use radians per seconds plot. So I multiplied the actual speed by 30 over pi. And omega here is a matrix. It's got all the different speeds for all the different slips. That's why we can have a plot. So this is just a scalar multiplication. Technically, I should multiply the 30 and I should put the 30 times P1 in front. But MATLAB is able to handle multiplying matrices and scalars in any order. Then I just plot it. And then this other stuff is just a searching thing that you don't have to go through 1 million entries to find it. MATLAB will do it for you. And that's how I got, well, it was there. Let's run it again. And then instead of 1 million, because it took a long time, would you be okay with 10,000? So I got 10,000. All I had to do was change this value to 10,000. You can make it even sexier if you wanted to and make it a value of a variable of n, and then you can specify. But you all aren't huge fans of MATLAB anyway, so I don't want to add more variables. So just put it there. And that's what that plot does.
So when you change 10,000, what changed on the graph?
Nothing. The graph looks the same.
Yeah, look the same.
What's the only difference?
Um,
How many points I had to plot to make this curve? I only needed 10,000 points. I didn't use 1 million points.
so that's the
Last resolution.
If you have like 10 points, you get 4.
You want to try 10? We have the power. How's that look?
Okay, yeah. Like what you got in the lab.
Well, we got in the lab, exactly. How many points did you take in the lab? I don't think it was that much. So all those curves, all those torque versus speed characteristic curves that you see for motors, they're all generated with, somebody has done a locked rotor test, a DC test, and a no load test. They got parameters for it, and then they literally just plot it like we did here. That's all they do. You cannot get this type of curve in the real world. But you have another way of plotting. Makes it pretty easy. So again, you don't need to be an expert at MATLAB. I didn't expect you to do any of this stuff over here. But the lines basically from here to here is how you calculated that. And then I had 2 or 3 additional lines, or maybe 4 additional lines to go ahead and calculate that. So maybe 15 lines, but that's just like you were doing it in your calculator.
Not much easier.
In your calculator is much easier?
I do today, but
Yeah, again, this is just, I like it because, as I said, if you look at the beginning, you see it says clear in CLC. That means it wipes out everything in MATLAB. Clear means all the variables are clear. So I didn't pull a fast one on anybody. It's all there. But I know Ryan had some comments, or maybe it was Ryan, maybe it was Dylan, I can't remember. But, you know, hey, we want to see less MATLAB and more of that. That's why I spent so much time doing this by hand. But as I said, I don't think you want to see me sitting here just typing numbers in my calculator. So I just use MATLAB, and then it makes it easier to follow from MATLAB. So I'm giving you both. I wasn't even going to go over the MATLAB file until Barzillai said, hey, can you spend some time explaining it? So. Questions?
are these fair game for me?
Yes, this will be the last bit of material that we can put on the test. So everything up to this point on induction motors,
Very good.
it's good to go.
There any more example problems? Area, without those different problems.
Air gaps?
Sorry, not so-
Well, I gave you some, I have some practice problems. I think there are 3 practice problems with this homework, right? Did you try those? Okay. Try the practice problems. Those are going to be pretty helpful.
Other questions about tests though,
What do you mean?
like these type of questions for the 3 different types of tests to find the parameters? Are there any other example questions for that?
Were there any on the homework?
I think the homework
Yeah.
review next week is some question about the,
Yes, I believe so.
you know,
I thought the homework was due today. It's not due today, or it is?
I don't know, the next one.
Oh, the next one. Okay.
What, is there the homework for the few?
I thought we had this one, but I could double check. I don't know. I have to look.
The one for today is already too recommended.
Well, we can't have another homework due next week, right? Because you have a test next week.
Yeah, but then I think that homework would be about repairs, right? Next
Yes,
one.
but the thing is, because we missed that day of classes, right?
Mm,
That put us behind quite a bit. But yeah, if you want, I can put up a suggested problem for how to do that. Sure.
Are we gonna have lab next week?
No, so that's it, right? You got a test. Normally we do the exam during that, but as a way to give you a chance to study, we don't have lab next week.
And then any lab for last week?
Probably not. I don't think we're gonna have enough time to get into anything new, so. Thought I saw another hand. Pat? No. We changing the rules? I thought we voted and we all, well, the majority ruled that said they are doing the test a week from Thursday. So a week from this, right now, during the live class. So
Tuesday will be.
Tuesday will be a review. I've already got this stuff posted. Thursday will be the test. You're allowed an 8.5 sheet by 11. You got an hour and 15 minutes. Take the test. And yeah, same guidelines. Yes, sir.
Is there, you always said one note sheet, but that's just one side of the paper, right?
No, you can use both sides.
Oh. I should have asked that 2 exams ago.
Yeah, the general rule of thumb is the more stuff you put on your note sheet, the less prepared you are. So you might be really super prepared. So it's a good thing. Oh, okay. No, but my rule of thumb is just like, if you know the stuff, you just need reminders. You don't need gobs and gobs of information. Because I find gobs and gobs of information get confusing. People in the past used to take all the slides and shrink them down to the 50 slides on one piece of paper. But I'm like, that's not really going to help you, is it? And they were happy with it. So I didn't. You can put whatever you want. I don't dictate. I just try to help people understand, like, is that really the best way to prepare for this exam? And sometimes they'd say yes, but the outcomes wouldn't always be the case. How about TV land? Any questions from TV land?
I think I'm good right now. I'll prepare some for Tuesday's class though.
Okay, I have one question, and it won't hurt my feelings at all. Does anybody want me to put this MATLAB script file up on the course folder today? Okay, then I will do it.
Yes.
I'm not doing it.
I
I'm
do enjoy
checking in just-
MATLAB, so
What's that?
I do enjoy MATLAB, so
All right,
Today I take more.
enjoy more. But I don't want to encumber you with too much information, so sometimes I want to check in, so, but okay. All right, there's nothing else. Have a great day. And I'll see you all on Tuesday. Take care, everyone.
thank you, you too, Paul.
Take care.